Yes, so it's 2 o'clock, at least in Europe or in Germany and France. And I'm happy to welcome you to today's presentation and webinar together with Metrologic Group. And I have also John joining me. Hello, John.
Hello, Jan.
Maybe just introduce yourself that everybody in this meeting knows to whom they are, who is the presenter today.
Okay, so hello everybody. We've got an international attendee list today. So good morning, good evening, and good day to wherever you may be and what time zone you're in. So my name's John Bryant. I'm the product marketing manager for the iRobot segment within Metrologic. So nice to see you here, and thanks for taking the time to join us today.
Yeah, maybe I just introduced myself as well. As you can see here, my name is Jan-Hendrik Lott. I'm the general manager of API in Europe, and I'm pretty close with Metrolog to find a good solution combining our hardware and the software of Metrologic iRobot. And that's also the reason we have our webinar today, just to introduce a little bit what can be done or what kind of measurement tasks can be solved using the combination of API products with the Metrologic software. And yeah, John and I, we spent some time a few days ago to prepare a short presentation and video. And I'm more than happy if you can share it with you and just give you some ideas about what we believe it's important, and especially if you are looking into applications for electric cars.
So we're going to play a video. It's about 16 minutes long. There's a Q&A window that you can use to post your questions, and then we'll be able to answer those after the video is finished playing. Okay. So here's the video.
Yeah, how the manufacturing changed in regards of electrical vehicles.
Yeah.
What do you think?
Mostly it's the same. People are still sitting in the car. We still have the body and weight around with the steering wheel. For now, maybe in the future we won't have a steering wheel anymore. But I guess that the biggest change obviously is the drive chain.
Yeah, most likely. Instead of a classical motor, we replaced the electrical motor. And instead of having fossil fuels and the fuel tank, we need to consider the energy based on battery and battery trays.
Yeah. So Jan, what do you think the important factors are for controlling battery trays?
I think the battery trays keep the battery protected. So the battery can expand or explode or damage, heat up. Needs more space, so the requirements to the battery trays are pretty high in regards of protecting the battery, but also if there's an accident.
Yeah, so in fact, yeah, that's right. There's a lot of security aspects to take into account for the battery tray, which is why the design regulations are quite high for manufacturing companies when they develop their battery tray, and which then means that they need to show and demonstrate that their quality inspection process takes into account the safety concerns during the manufacturing process. So the inspection process needs to be well adapted for the measurement.
Hey John, what do you believe is the most important characteristics for such a solution?
Yeah, so it's still early days with battery tray technology and innovation. There's still processes and materials that are changing constantly based on the different needs of the vehicle being designed, how we store the battery cell, the types of material. So I think flexibility is going to be a big key.
Yeah, I guess the flexibility is the main key element in the current manufacturing. As you said, the materials change, so you need a sensor who adapt to different materials. You need to be fast and flexible in the modification of the program depending on some new findings.
I think that makes it important to have a system where you can move the sensor, because based on the size of battery tray or the the different accessibilities for your measurement. Having a robot that can potentially move the captor to different locations is a key aspect.
Yeah, I agree. But obviously, the electric car manufacturers are still looking for the best solution. There are already some solutions in the market, but nothing really fits all the requirements we just talked about.
Let's take a closer look at what we have in the setup behind us here.
Okay. For a solution for the customer, it's always interesting to start with the hardware. The hardware, in this case, is the API 90 LADAR. It's a scanning system. It's scanning the surfaces. The chirp interferometer, which is the core model or core technology of the LADAR, is able to detect different surfaces. We talked about earlier that material changes. Such kind of sensor is able to just adapt the same measurement task to different materials. Then what you see here, everything is included. So we have a small compact system. It's just 11 kilograms. So we have a huge robot here, but it's more about the size to measure this battery tray, which is, by the way, loaner from the company Calcul in Germany. Thanks for that. And yeah, the weight does not require huge and heavy robots. Then we have a high-speed scanning, which is in line with the requirement to have fast and reliable measurements. And all this stuff can be easily controlled from the software. So the 90 LADAR with a small weight and a high incident angle allows us to really get the battery tray measured quite fast. The incident angle of 85 degrees or up to 85 degrees allows us to really scan surfaces which is more or less quite steep or parallel to the surfaces. We will see it later on in the scenario, how it works and how such kind of technology simplify the complete process and speed up the complete measurement. And as said, the hardware is one part, but the software is the second part of the solution, and I hand over to John to explain how Metrolog X iRobot can help.
At Metrologic, we provide a software solution for our customers. Our goal is to simplify the 3D inspection process. For that, we've developed a product, Metrolog X4 iRobot. The goal of Metrolog X4 iRobot is to control the robot, trigger the sensor, taking into account its different characteristics, such as angle of incidence, distance from the feature being measured. Then once we have the 3D measurement data coming back from the sensor, we're able to perform the analysis of the point cloud to determine whether the part is good or bad. And then depending on what went wrong, if it was a bad part, being able to suggest how it could be corrected for the manufacturing process. Because measurement data is good, but if you don't use it to correct inconsistencies, then you're not benefiting really from the data. Also, we have two versions of the software. The first is Cinema, which is our offline tool, which enables us to simulate the process without having an impact on production. Once we've validated the program, we can then deploy it online, which enables us to have more uptime on the robotic cell.
I would suggest we have a look into the reality, how it looks like. From the beginning, we receive a CAD model, we need to define the program, we need to define the feature and inspection points, and how we can utilize the robot, the LADAR, and get the complete process done.
So this is a pretty classic scenario. We've got a supplier who've just received a CAD file from an automotive company for a battery tray. And they're asking the supplier, okay, we need you to make it. And then if you make it, you also need to control it. So here we are in Cinema, which is, as I mentioned before, our digital tool. So it's the digital twin of the existing cell that already exists within the company. We've opened the CAD file. There's no GV&T data embedded in the CAD file. So we're measuring the characteristics that we believe are important. We're starting here with the corner circles that anchor the battery tray to the chassis of the car, and they're going to be used eventually for alignment purposes of the part. The blue squares you can see, they're the simulated point cloud coming from the simulated LADAR. So that simulated point cloud is what allows us to generate already the tickets, the labels that you can see. So we can generate the report, simulating the point clouds that we come back. In Cinema, they're all perfect, of course, because we're not adding any variation to the point cloud. They're all matching well with the CAD file. But it allows us to create the template for the report, so that when we do deploy it to the physical cell, we've already got something that's functional. As you can see here, the report is coming up with the numbers that are displaying green. Once we have the program, or happy with it within Cinema, we can deploy it online. So the Cinema aspect was all done within the comfort of our office with air conditioning. Now we're deploying it on the shop floor. There's a bit of noise. We want things to move quickly. We don't want to spend a whole week deploying the program, because it means that's a week we're not using the cell to measure parts. So it's all about deploying quickly onto the shop floor. We can see here the LADAR, he's measuring the tooling balls that are placed on the wall. That creates the station for the LADAR. Once we know the position of the LADAR, we can then measure the parts. So before we start by doing alignment, and here we're jumping to measuring directly the features. Here we can see with the program that we created, there were 2 stations required to measure all the features of the battery tray. And just for the demonstration here, we show the LADAR upside down to show that you can measure any angle with the equipment. And then once the measurements are done, we can see the results. And this is using the same report that was generated within Cinema previously, where we saw that the manufacturer had the autonomy to receive the CAD parts and create the trajectory of the robot, control the sensor to measure the parts. And they could do that all without having to make a call to a third-party service to control the robot separately. We had a synergy of how the sensor worked with the robots, meaning that we had a really fast and efficient measurement of the parts, which is critical when we're in production for the customer.
Yeah, we have seen how it looks if you start the process from CAD model into the final measuring cell, but the reality shows you need to adapt the program during the process. So let's have a look into the second part, how we can adapt the existing program and adjust it and add new features, new requirements.
So in this scenario, nothing's perfect straight away, unfortunately. We've started manufacturing our battery tray, and we realized that some of the surfaces aren't flat, and so the battery cells aren't stable. So this is a fabricated scenario, but we wanted to give you an idea of, okay, we have a problem in production. Now we need to modify the program in order to measure some new aspects of the part to make sure that those problems are being resolved in manufacturing. So here we're using what's really good with the LADAR is the surface scan. So we're creating a surface scan within Cinema in order to measure the flatness of the battery tray. Hopefully we can correct those issues now in production. So again, the blue that we can see there the simulated point cloud coming from the LADAR. And we'll see shortly that we can also modify the reporting template in order to display that new information. And these are the types of challenges that we can imagine happening within manufacturing. Nothing's perfect straight away. There's always some adaptation. We need to be flexible, and being able to control your own program internally is a huge advantage to reducing that cycle time of updating program and then going to the shop floor. And so here we're deploying the updated program onto the shop floor, and we're going to see the trajectory of the robots now taking into account that new feature that we're trying to measure. So what's happening here is that we do just like before with the previous program, except now we've modified it. We've added some new characteristics, some new features to measure. And so it's a continuity of the existing program that's been modified. Depending on your connection speed, you might be able to see the laser, which is scanning the tray there. Which gives you an idea of the speed of the mechanism. Okay. It's battery tray innovation constantly changing, and it's new innovation, new technology. We need to have that flexibility to adapt the process in function of what types of problems that we encounter. So that was a great example of how we saw an issue and we were able to adapt the program to address the issue in production. So it enables us to be reactive and flexible, which I think is a key aspect when we're doing manufacturing.
Yeah, but the battery tray is just an example. So for sure we have a lot of different applications in the automotive, but not limited to the automotive only. I have a lot of ideas about aerospace and renewable energy, for example, where we can use the same solution, just adapting to other parts and requirements.
Yeah, that's right.
Okay. Yeah, I think, I believe the presentation or the video shows at least the workflow, how a typical manufacturing process or measuring process looks like. And right now, John and I are more than open to answer some questions which are raised up during the presentation, or maybe you have some dedicated questions to your own application, to your own measurement task you want to raise up yet. For sure, if it is a little bit more confident, you are always able to reach out to John or myself directly, and we can discuss it in a small group. So just see or check if there are already some questions available. So you can use the chat, or if it's a little bit more convenient for you, the Q&A button at the end or on the toolbar of Zoom. So far, Jon, you want to add?
So I have a question. How much of the programming can be done offline in the simulation software? So in terms of, I guess the question is, how realistic is the digital twin within Cinema compared to the reality? So within Cinema, we can simulate the density of the point cloud. We can simulate the characteristics of the measuring device. So as Jan mentioned, we have the 85-degree incident angle. After that, we're not going to get, we're not guaranteed to get a good measurement. So we can take that into account within in the simulation, and maybe change the color of the point to show that it's not valid. We can also determine the line of sight, if there's any CAD files that show fixtures that are blocking access to a feature. So there's a lot of things that we can simulate in that process to make sure that we win time within Cinema before deploying it to the manufacturing floor.
Yeah, see, during John explained the first question, we got some further questions coming in. One question I can easily answer is, can the LADAR measure in any position? Yes. As you may see in the video, the robot moves to different positions, and you can use it in a horizontal way, upside down, whatever position you need to reach your measurement points. There was another question, which I hand over to John. Is this solution compatible with the data loop?
Yeah, so Data Loop is an open platform, and they can accept certain formats. And within Metrolog, we can export. We're also an open solution, so we can export the point cloud or the results in a certain format. So yes, there's definitely some compatibility between the solutions.
Okay. Good. Hopefully this answers your question. There's another question which came in. Does iRobot check the collision for the beam when measuring the part? I think it's also something for you, John.
Okay, yep, thank you. Yes, so there is collision detection within iRobot. So we call it not just collision detection, but also collision avoidance. So when we're creating the trajectory of the robot, if we have a beam in the way, then we'll make sure that our trajectory goes over the beam, or the most efficient trajectory to avoid a collision. So when we do that using bounding boxes around the aspects of the CAD file to ensure that there's no collision between the robot or the sensor and the part.
Okay. I just want to raise up the second question here in the chat, but Carsten already answered. Yeah, flash and gap is a typical application, can be solved by the LADAR. The advantage of the LADAR is maybe also in this regards that we have a quite high incident angle, so up to 85 degrees, which allows us, especially for flash and gap applications, to get a lot of points also around the curve and in the, let's say, inner side of the flash and gap. So yes, for sure, that's a perfect application for the LADAR. There is another question in the Q&A, which belongs to the pricing. If the LADAR is still at 350K, we were never at 350K, but if you want to have dedicated pricing, please reach out to me directly, and we can discuss the current pricing of our systems.
Here's another question for Jan. How does the solution pick up reflective or clear surfaces?
Actually, the laser which is used is a chirped laser interferometer, and is quite insensitive against surfaces. So you might have seen also in the video that the battery tray have quite reflective or shiny surfaces in the plane area where we put the second part of the scan. This is not a problem, and also clear or reflective surfaces can be scanned. Yes.
Which may be an important point if in the future battery trays or other parts like carbon fiber like a glossy dark finish?
No problem. Especially, to be honest, I was really surprised by myself what kind of surface we can scan, and black, white, shiny. There is more or less no limitations. For sure, there might be some surfaces which can be a challenge, but it is always a chance to try it. Okay. Yeah, for sure. That's exactly what we ask you to do. So please feel free to reach out to John, to myself, for personal meetings, for webinar. We can also do some online checks, some discussion about your application. Whenever you want to reach out to us, feel free. We will forward it to the right region. So I see there is a request for Canada. That's for sure something my colleagues from the US can support you easily. And if there's something in Europe, I'm more than happy to support you directly. If it is for the other regions from, let's say, from China to Hawaii, API has local offices in all larger regions, so we can get easily local report and support you with your requests. I think same for John. Metrologic is well established worldwide, have a couple of partners, so it's easy for you as well to support worldwide, right?
Exactly, yes. We've got a worldwide presence, a sales office in America, in India, throughout Europe.
Yeah.
We also have another question. Can the solution be used for turbine blade application? So I think there may be two sides to that. I'll let Jan start with the hardware side, and then I can jump in with the software.
From the hardware side, for sure, yes. No, it's a perfect solution. We have, I'm not sure about the size of the turbine you are looking for, but for sure, if it is visible, we can easily do some scans of the blades. We can do some detailed scans of some special areas of the blade. And it's a quite interesting application. Advantage maybe if it is a larger blade, which is difficult to access for tactile measurements. The LADAR can measure up to 25 meters. So you can put it on the floor and scan the surfaces up to a higher angle where you don't need to have any considerations regarding safety requirements for the operators. So I think, yeah, it's a perfect match for the LADAR. And I think to head over to John, and it can be done with Metrolog, right?
Yeah, and so within Metrolog, so for sure, a turbine blade often has certain types of properties to determine whether it's fit for purpose, and we have a module just for that purpose to measure blades. So it's something that we can definitely address within the software.
Okay. Good.
We have another question for Jan. Can the LADAR be serviced in Europe?
Yes and no, depends on what kind of services is required. Actually, the system is developed in our headquarters in the US, but we have the first level service like certification established in Europe soon. So we will be able to get the first level support here directly in Europe right now. But for the future, for sure, it's intended to extend the services to a higher level. Okay, there's one last question maybe. We just need to look a little bit to the time frame. The application requires 50 microns accuracy. Our LADAR is specified to 15 microns plus 6 microns per meter. And this is quite challenging to really say yes or no. I would like to get more details about your parts and the materials to really give you an answer. But also here, feel free, reach out to me, maybe send a picture or some details. We can look into it and clearly state if it is or what is the closest capability with our systems. Okay, I think time is over yet so far. For sure, if there's any other question, reach out to John and myself. And this said, I would thank the Metrologic team for the support here in preparation for this webinar and for the participation for sure here today. And I'm really looking forward to further discussions with you or some customers coming up with some new ideas and questions. Feel free to come back to us. And yeah, in this case, I wish you a nice afternoon, evening, morning, wherever you are. Enjoy the day or the night. John.
Yeah. So thanks a lot, everybody. And again, if there's any questions or if you have any queries, feel free to reach out to, as Jan said, to himself or myself. We'll be happy to answer any questions that remain. So thanks a lot for your time.
Yeah, thanks too. And see you. Bye-bye.
Bye.